Good afternoon and welcome. I'm Brent Donaldson, Senior Editor for Modern Machine Shop and for Additive Manufacturing Magazine. Today's webinar, brought to you by Okuma, is aimed at successfully delivering your products faster, better, and more competitively than your industry counterparts. While working harder can deliver some results, working smarter more often provides the needed competitive edge. By integrating the right machining and automation technologies, manufacturers can drastically increase both production levels and revenues. Primary topics for today's session include using technology to reduce direct labor cost and operational expenses, comparing manned and automated production operations, developing consistency by standardizing processes, and previewing select integrated technologies. Today's presenter is Wade Anderson, a machinist by trade who started programming machine tools in 1992. Wade's early years were spent working for companies machining large, heavy equipment components. Wade became an applications engineer for a machine tool builder where he spent 11 years developing super abrasive aerospace and medical processes with an emphasis on 5-axis grinding. He did a lot of 5-axis programming and machine tool troubleshooting, even building machine tools from the ground up. Wade joined Okuma America Corporation in 2005 as an application engineer and moved from there into inside sales, sales engineering, and regional sales management. He was recently promoted to product specialist, sales manager, and tech centers manager, where his diverse background enables him to help Okuma's distributors and end users go beyond their manufacturing challenges. Please note that you can submit questions for Wade at any time during this presentation. Just type your questions into the questions box and we'll answer as many as we can at the end. Also note that this webinar is being recorded and you will receive a link to that recording via email. With that, I'll turn it over to Wade.
All right, thank you. Good afternoon, everybody. I really appreciate everybody taking time out of your busy days to join us here this afternoon. So today I'm going to go through kind of the building blocks, if you will, of what you need to look at in terms of integrating automated processes into your system. So this is basically my agenda slide. This is going to be the roadmap for us here for what I'm going to talk through this afternoon. We're going to touch on industry pressures, where we see the growth, types of automation in terms of what we use from custom integration versus OEM type automation. And then what I really spend the bulk of my time on is really the considerations, things that a lot of times people overlook when they're looking at adding automation into their process. And then we'll go through a quick overview of a justification example where you can see some of the return on that investment. So some of the common pressures of industry, I'm not going to read bullet point for bullet point. Everybody here can read faster than what I'm speaking. But the general consensus, if you will, I get to talk to thousands of machine shops every year, and there's a common platform, if you will, that I hear from customers over and over of areas that they struggle in or areas that they are feeling pressure on a daily basis. And at the end of it, when you look through all these bullet points, at the end of it, it's how do we do more with less? How do we get more productive with our processes? How do we do more with what we currently have? How do we bridge the skills gap? So some of the things that's common in the industry, everybody has people. Every machine shop has equipment and tooling. Everybody deals with certain types of materials. And everybody has financial resources or at times financial restraints, depending on what the situation is. So these 4 bullet points really encompass the level playing ground that everybody is on. But what really sets manufacturers apart from their competition are really your individual unique processes. What is it that you do differently that sets you apart from the job shop next door or your leading competitor that you're going to market against day in, day out? So your processes and what you do, your intellectual property, if you will, is what really is going to set apart your manufacturing process from those that you compete against. So one of the things I talk to customers a lot on whenever I go to visit machine shops is what is their current spindle utilization. And sometimes it's shocking. I will say there's definitely a big trend as people are taking on and embracing software that's helping them to automatically collect this data. But most people think that they're running a higher spindle utilization than what they truly are once they start measuring it. So this is a survey that was done based on 100 plants, both large manufacturing facilities as well as small, what we'd consider your 20 people and under job shops, to see out of 100 shops, what is their average spindle utilization. And that came out to 34%. So roughly speaking, just round numbers, a manned machine where you've got an operator running that machine will typically run 3,000 hours out of an available 8,000 hours available over the course of the year. So that 34%, that's the number that we want to look at. How do we drive that forward? How do we increase that number and get up into 50, 60, 80% and higher ranges? As we look at employment throughout the nation, the continental U.S. has a really good growth pattern right now. So one of the talking points, I like this information. I like seeing maps like this. One, I like to see growth. That's good for the overall economy. It's good for the country. But I'm one of them. I'm sure there's many on the phone today that lived through the 2008, 2009 time frame. And even during that time, when times were really tough, really lean, there were people losing jobs, there was a lot of unemployment. Even during that time, machine shop after machine shop that I went and visited and worked with had a common theme that they couldn't hire skilled labor. Even during a time when the recession was in its kind of full stride, people had a hard time finding skilled labor. Today, it's even that much worse because the economy is strong. The growth employment throughout the nation is really strong. You look at the Southeast and the Southwest especially has seen tremendous employment growth. So it's even harder to find that skilled labor, and that's where automation starts becoming a primary focus for companies like us, who is a actual OEM machine builder. We start looking at, okay, how do we help bridge that skilled labor's gap? As we look at the automation industry as a whole, the graph on the left, that blue line at the top, this is representing machine tools, and then the line on the bottom, the orange line, is representing the machine tools with automation that's sold. So even though sometimes the machine market, appears to have kind of a flat trajectory, the automation side of it has been growing. If you look at the graph on the right, you can see a steady growth trajectory across the board of automated equipment that's been purchased from 2011 through 2017. This is just a very nice linear growth trend, if you will. So I'm going to step through the types of automation that we typically look at on a day-to-day basis with customers. I'm going to start with the very simple. Most machine shops, anywhere you go, you're going to see bar feeders hooked to a lathe. This is sometimes overlooked from an automation perspective. However, there's a lot of times we'll go in and look at what a customer is doing when he's slugging parts or loading in individual unique castings, and you start looking at the process that he's doing and where his bottleneck is, a lot of times on the setup time. And many times we can look at ways that we can get multiple types of parts out of one common platform and bar feed those applications, and we can whittle chips faster than you can have a machine down in the middle of a changeover process. So many times when we're just looking at how do we make these incremental steps to increase productivity, a lot of times it's looking at an application that a guy may not be bar feeding, and we can look at that, add a bar feeder, and actually change his mentality of how he's making parts currently. The picture to the right, that's a horizontal on an FMS system, flexible manufacturing system. Typically we work with companies like Fastums from a FMS standpoint, but this is an area where you could tie in a single horizontal, vertical, or 5-axis machine, and then grow as your business is growing. You could plug in multiple machines and keep adding these pallet systems. So that's an area that we look at. These are typically, and I'm going to say in a broad brush stroke, typically third-party type options. These are bar feeders are built from companies like Edge, LNS, IMCA. The Fastums FMS system would be something we would use with horizontals. There's companies like Liebherr that offer very similar systems. So those are areas that most companies, even ones that are painted and they look like they match the machine, generally speaking, they're built by a third-party company and integrated into that system. Then when we look at OEM, what I'm going to kind of bill as the OEM type automation systems. Generally speaking, we're looking at pallet pools on machining centers, and then gantry or other types of robotic type loading on turning centers, whether it's multifunction or straight live tool Y-axis type turning systems. So our pallet pools, these are items that we build from the factory. We bring them in, and we'll typically do pallet pool systems single, dual, or triple level, so we can go from 10, 6, 8, 12 pallets at a time. And then those are typically cells that are set down in place, and generally speaking, that's one machine with one pallet system that gets added. Where you look at an FMS system, you're adding multiple machines to one linear pallet system. Gantry machines, the picture I have here, that's one single machine with one single gantry. However, this could be an automated line where you have 6, 10, 12 machines tied in with one gantry beam with multiple arms feeding the machines coming down the line. So these can be customized depending on what the customer application is. And then we get into, generally speaking, when you say the term automation, where most people's minds go is with the robot tending systems. So I've got two different versions here that I'm going to talk to. The picture that I've got on the left, these are what I bill as application-driven automation systems. So these are custom engineered systems based on customer specific needs. So this could be, again, one robot loading one machine. It could be one robot on a rail system loading multiple machines, or an overhead gantry beam with a robot loading multiple machines. So those can be very flexible and customized to the applications. The machine on the right, that's showing what we call a load and go system from Automation Within Reach. That is a standard kitted package that has either a drawer cell or a rotary type table system on it. It usually has one or two robot options, so a smaller, lighter robot capacity versus a bigger, heavier robot capacity. But the unique thing on this is that is something that really the customer can integrate on his own without needing custom automation or custom integration to the machine tool. So a load and go system like this one comes pre-programmed, and it has a conversational language that a customer uses to actually teach, or teach is not the right word, but tell the robot what type of work he's loading. Is he loading bar work? Is he loading flange work? Is he grabbing the ID? Is he grabbing the OD? Once you set up a series of parameters through a conversational piece, all the robot movements going from the load and go to the actual center line of the table, or the vise on the machining center, or a chuck on a lathe or a grinder, all those systems are already pre-taught. So once you connect the interface, go through the conversational program on how you're gripping and where you're unloading the part, all the teach points are already set in the system to be able to plug and play to the machine tool. So we recently watched an install on a customer's floor where they brought the system in. From the time they dropped the pallet jack out from under the load and go system and got it unbanded, it took them 4 hours to have the machine into production with an automated solution. So those are very unique systems to be able to use to kind of get started in automation if you're not already using it. So some of the considerations that you need to work through when you're looking at how are you going to automate your process, or what the correct process should be to automate. So these are just a bullet list that I go through every time I'm working on a project with a customer. We start at the top and kind of work our way down. We start looking at what type of machine does the customer have. Are they reliable enough for the process that he's doing? You know, obviously, if you're trying to hold tenths, and the machine tools you have will only hold accuracy that you can measure with a tape measure, you got a problem right from the start, right? So you want to make sure you have good, repeatable, reliable machine tools. And then you got to look at the strategy. What's your strategy for actual production? And that starts from looking at what is your short-term goals, as well as what are your long-term goals. What are you doing in the next 3 to 6 months? And then what are you doing in the next 5 to 10 years? Where are you trying to take the company? And make sure you're putting a system in place that is going to help you get to where your long-term goals are. Then we're going to work our way through fixtures, cutting processes, coolants, making sure we've got all of the variables controlled. Anytime we're automating, first thing we've got to do is make sure we have control of all the variables. If you have something that you don't have control on, you will not be able to successfully automate that process. So when I talk about coolants and fluids, for an example, a lot of that has to do with chip control. If you're producing long, stringy chips that are not repeatable, you can't automate that process. You need to be able to break chips and have small chips that are manageable and breakable, that's repeatable, that you can be able to automate that process with. If you're getting stringers 1 out of every 25 parts, you're going to have a problem if you try to automate that system. Then we get into quality. Having a closed feedback loop is very important. Scheduling, tracking, be able to visualize and see what's taking place on the floor. And communication. Communication, whether you're talking about dealing with people, if you're a manager trying to manage a team, or whether you're trying to talk about machine tools and automating systems, the root cause of most failures comes down to communication and being able to have good, solid communication ahead of time before problems happen. So let's peel the onion a little bit and talk about the strategy. I'm a big fan of multifunction machines. Obviously, at Okuma, we produce a very broad line of various multifunction machines. However, that's not the answer for every process that's in the manufacturing world today. There's many times you can look at a process and go, oh, that's a great part to be on a mill-turn machine. But if you look at the long-term goals and the strategy of what the company's trying to accomplish, there's cases that can be made where you need to say, you know what, instead of doing that all in one, all and done one-time machine, we need to go back to a op 10, 20, 30, 40 type setup and work out a production system. So this, again, goes back to what do you need that's going to move the needle for your facility. So just a very quick, simple math routine that we do to look at what is going to be the best process. This is just an example. Obviously, your individual processes are going to be a little bit different, but just for an example, in this case, if we're looking at a conventional type setup where we have 4 machines, the setup time is 9 hours. The tack time in this example is 0.9 hours versus a multifunction machine. The setup time we can drastically reduce, even though sometimes the tack time may be a little bit longer. A turret lathe, for an example, is going to change tools a whole lot faster than a mill turn lathe would. So your tack time is a little bit longer on the multifunction part, but you're saving time on that setup time because you're able to catalog a library of tools in a tool changer. You're able to do more work in one setup, things of that nature. So we reduce our setup time. So in this example, if we take our setup time over our run time, we come up with a break-even point based on these numbers. You come up with a break-even point of 41 parts. So that means if I'm doing parts 1 through 40 and then I'm changing over, or I'm doing lots of 20 or 30 parts at a time, I'm going to be faster overall on a multifunction machine. However, if I'm doing lot sizes of 10,000, nope, I'm going to outrun you all day long in more of that conventional type process. So again, this is going to be different for everybody's manufacturing system, but there's simple math that you can look at to see, okay, which way do I want to go? And obviously there's more considerations in terms of work in process, fixturing, things like that that's got to come into play. But just generally speaking, if you're trying to get a starting point on where do I start with my process, this is a great way to kind of get the ball moving. Then we start looking at fixtures. I'm going to show a couple of different examples from workholding and show a couple of different companies that I do a lot of work with. This example, I'm talking about Jergens, big fan of their 0-point systems. I like, if I'm working on a automation system, I want to have as much commonality as possible. So in this example, if my end of arm tooling is grabbing the same type of base plate, so my pickup diameter, my pickup location is the same all the time, I don't have to change my end of arm tooling as much. So if I can have that common platform where I'm using a base plate with a receiver in a 0-point type setup, then on top I can mount any type of fixture, any type of work holding that I want, and it doesn't affect what my robot end of arm tooling is. So the more I can try to standardize and have a common platform, the easier it is to move that same part or that same base plate around my shop. When I look at fixtures and work holding, I like to look at, one, what is the customer trying to accomplish, and then are there better ways of doing it? So when I look at hydraulics, I do a lot of work with machining centers and horizontals, and we still use a lot of through pallet hydraulics and overhead hydraulics. I will say I'm a big fan. I've used a lot of these fixtures that are in the top picture, this North Heartland tool. This is an example of a blade, aerospace blade fixture. It's a 6-point nest. The thing I like about this is that is a self-contained hydraulic fixture. So I would mount that onto that base plate of that Jergens 0-point system or a Schunk Bureau S system. I would mount this fixture to that base plate, and then my robot end of arm tooling would be grabbing that base plate and moving that in and out. So then my top tooling, that could change depending on what my parts are. But the thing I like about this is that can be self-contained hydraulics. I'm not dealing with overhead hydraulic systems. I'm not dealing with through pallet hydraulic systems. Anytime there's maintenance, I'm not shutting a machine down. If I spring a hydraulic leak of some form or fashion, I can quickly work on this fixture and replace an O-ring or something like that, and I haven't stopped my spindle. I can have other work in that machine still running. So I'm just a big fan of systems like this. Anytime I can simplify the amount of moving parts, the better. As we talk about fixtures and work holding, being able to make sure that you are seated and that you have confirmation that the part is loaded correctly. This is an example of a tombstone style fixture or a base plate that would go on a tombstone. This is from Bushy. We do a lot of work with Bushy work holding, especially in the automotive industries, things of that nature. But incorporating air seat confirmation to provide feedback to the control to let you know before you put a cutter on that part, is that part clamped? Is it in there correctly? Was anything misloaded? Be able to catch that ahead of time is what's going to keep that automation system running. Chip control, I mentioned earlier about being able to control chips and make sure that you're not leaving stringers in a lathe, for an example. This is another thing when it comes to machining centers, making sure you have chip control from a machining standpoint, having built-in air blows or coolant nozzles that can blast the seats of your fixtures where parts are going to be loaded, things of that nature. These are very important considerations when you're looking at fixture designs and how are you going to hang on to that part. It's one thing to have a fixture where you can hold the part repeatably, but you also have to consider what contaminations could get in there when an operator is not standing there putting his eyeball on it. So being able to have that built into that fixture system is very important. Manual decouplers. This slide I like because, one, it talks to being able to have parts where the robot can charge and uncharge the fixture on certain models. So if you've got a hydraulic machine, a horizontal machine, you're running hydraulic fixtures, there's ways that you can incorporate that into the end of arm tooling from the robot. And then there's pressure gauge indicators. There's simple things that you can do from a fixture design standpoint. In this example, what you're seeing there is a little button that pops out when everything is pressurized and clamped correctly. That little pressure indicator will have a button that'll pop out. You can quickly come in and have a probe touch that and say, okay, is that button there? Yes, I'm clamped, everything's correct. If it's not there, wait a minute, something's not wrong, not right, and flag the machine, have an alarm come up. flag the operator, come and check what's going on, or shuttle that part out, shuttle a different part in, and send that to a setup station to have it checked out. Part retention, another consideration when it comes to fixturing, is making sure that you have a way that you can typically spring load the part. So the robot, if you're actually using the robot to load the workpiece, have the robot bring it in, have spring retention clamps to hold that part in place while the robot gets out of place, loads the second part, and then hydraulically charge these. These are very popular when it comes to your more automated, high volume type production, automotive environments, things of that nature. Another consideration are redundant tools. Too many times I see automation cells in the field and the utilization is not as high as what a customer would like, and when you start boiling down to the root problem, it's because the machine is sitting idle waiting on an operator to come in and swap inserts or change a tool that expired, things of that nature. So being able to make sure you've got a library that has multiple redundant tools is very important, depending on the length of time that you're wanting to run, as well as the type of materials. If you're running aluminum, it's not as critical. If you're running titanium, Inconel, it's very critical. So those are things that you've got to look at. Some unique ways to get more redundant tools. My example at the top, one, if you take just a single turret lathe, for an example, just simply jumping up one step of technology and going to a twin turret lathe. Even if you're not pinch turning or doing operations where you're trying to combine operations into a machine, adding that second turret gives you more tooling stations. You jump into what we call our LT platform, where you tie in 2 or 3 turrets. Again, you're doubling up or tripling up the amount of tool capacity that you have. So those are some sometimes overlooked options. And then a big one is just simply, if you're talking about a turning application, adding a Y-axis to your turning machines. I've walked into shop after shop and we're looking at their process, and they've got a live tool machine that's just an X and Z axis, and you look at the incremental step in productivity gain they could accomplish simply by adding a Y-axis. That not only gives you capability to do geometries that you sometimes have to take over to a mill and second op it, but it also gives you opportunities to double up or triple up the amount of tools that you have on the turret station. You could take one tool position and by shifting it in Y-axis, add 2 or 3 different cutting tools into that one same pocket, provided your part has the geometry that allows for that. There's one customer that we've got out in Arizona, and it just extremely highly intelligent machinist. He created his own tooling block, and he has 7 different cutting tools in each block, utilizing his Y-axis. Now that's extreme. That's way over the top. That takes somebody that's got a lot more creativity than I've got. But just having that one additional axis can open up a big change. Having multifunction machines, again, anything that's got an ATC, horizontals, anything where you have an ATC capacity, you have opportunities to add multiple redundant tools. If you're going into an FMS system, first step, you want a large ATC typically, or go to a Hive system from the FMS provider, so you can have multiple tools. Game tools or flash tools are very popular as well in your mill turn style machines, where you can index the milling turret, or the H1 turret in our case, to have multiple cutting tools in one type of tool. I mentioned feedback. This is something very critical when it comes to automating processes. You don't want to have the cell shut down for something, probably not the most politically correct term, but for something stupid. So in this example, I'm showing just a very basic system. This is showing coolant concentration. So the picture on the left is our OSP control with Okuma monitoring system and a couple of different applications that it's monitoring. But the pictures to the right, that's simply checking coolant concentration. So I can keep track of what's taking place in that production cell. It's running production. I don't have an operator there tending it all the time, but I still want to make sure I'm maintaining that machine properly. So this is one example of just something very simple to do. Another one, way lube. You want to get ahead of these things. If you've got a machine that's constantly running out of way lube at 2 o'clock in the morning and shutting your cell down, have this monitoring system monitor that and get ahead of it, and let the operator know before he leaves, or your maintenance guy, whoever's taking care of fluids, to know, hey, at 3 o'clock that afternoon, make sure you go and add these fluids. The monitoring system will tell you how much runtime you've got left before you're going to wind up shutting that cell down. A simple thing like chip conveyor. I've got a sensor on the shaft of the chip conveyor to confirm that chip conveyor is turning. You don't want to, again, a stupid mistake where somebody walks away, the chip conveyor stopped, or you wound up with a bird nest of chips that jammed up in a system, and you overflow coolant, you got coolant all over the floor, and you got an automated cell shut down because you got a $25 an hour guy out there mopping the floor because of something simple that could have been caught up front. So these are all just different things that are very simple to monitor, that sometimes are overlooked, but can make a huge impact in the productivity of that automated cell. Quality and part inspection. One of the great things of automation is you automate the cell and you can make a lot of parts. So now, do you want to make a lot of good parts, or do you want to make a lot of bad parts? That robot doesn't care. It's up to you and the system that you design to make sure that your manufacturing process is delivering good quality parts. So having in-process gauging, everything from a very simple touch probe in the machine, very, very common today, all the way to tying in, this is a picture of a Renishaw equator. It's a phenomenal comparator to have on the shop floor to compare parts, and then tying in these systems to your tool life and your work offsets, so you can trim the parts and let that system automatically make offsets as needed to keep parts in tolerance. Again, taking that out of the hands of a needed operator. Let the system do that work for you. All the technology is out there. It's just got to be utilized. So in this case, Karen AutoComp, you set up work in process tolerances. It will trim that, and when it gets to your limits that you've set for your work in process, it will offset your geometries to bring it back in. If it realizes you've made too many offsets, you moved it more than a predetermined amount, it will flag that tool as, something's wrong. You've got a broken edge, something of that nature. Call up a redundant tool or flag it for the operator to come check and see what's taking place. So these are all systems that needs to be incorporated into any type of a automated system. Making sure you're connected, regardless if you're automated or not, you should be connected and monitoring what your machines are doing. We have software, we call it the Okuma Smart Factory, where we can monitor what everybody bills, your green, yellow, red lights, right? Is your machine running? Is it down? Is it waiting on an operator? Things of that nature. But also, what machines need maintenance? Do you have a machine that's got a maintenance issue taking place? Things of that nature, so you can send emails or alerts to flag the right people to get involved with it. And again, that's regardless if you're automating a system or not. Just being able to monitor and measure your productivity. We work with companies like 5ME, Freedom E-Log, Memex. These guys do a phenomenal job monitoring anything that could be basically MT connected, monitoring that equipment and providing that type of feedback. Again, going back to scheduling that maintenance, if you are talking about an automated system, you can't ignore the maintenance, and you want to build that into your process, into your system, so that you don't have unexpected downtime. You're getting ahead of it ahead of time. It's terrible to see a machine tool get shut down because of something very simple that could have been caught 2 weeks earlier. So these are ways to predetermine, have periodic maintenance predetermined into the control, and build that into your ERP or your MRP system to be able to schedule that into your production system. So a couple of different examples from an application-driven aspect. Again, these would be kind of your custom integrated systems. So this is one example. This is a pinion manufacturing where there's no changeover. So they're going from, I think there's like 40 different types of part numbers, and no operator does any changeover in the system. It's bar feeding raw stock in, and then the robot is unloading and then sending it to various stations. So what's pictured here is a shop floor CMM that's doing all the inspection. There's cases to have engraving if you're, or laser etching if you're doing serial tracking. You can do deburr stations, wash stations. Really your imagination's the limit of what you're going to do in that cell, depending on what your processes are. So that was the concept picture. This is kind of the picture of it in full operation. Again, you can see the bar feeder tied to the lathe, and then the shop floor CMM, and then the entrance area into that robot cell has laser light curtains. So the guy gets it within X amount of feet, it will slow the robot down. If you break that light curtain, it will shut that system down and wait till somebody is clear. But these are custom type applications that we do a lot of cells with over the year. This is an example. Sometimes people believe that you have to have a very expensive process to justify automating it. This is an example where they are literally just turning the diameters of the ends of tubing. Probably the simplest type of machining work that you could possibly do. And the machine tools was actually the cheapest part of the entire cell. They've got over $1 million invested in the automation system, but they automate this entire process in this entire cell where it does the part picking, it loads the stock, it brings it in, it does all the measuring and inspection. And these robots are mounted behind the machines, and they reach over the front into the door, so the operator still has full access to the front of the machine. And then because this only uses one tool for the cut, they've got all 12 stations loaded up with redundant tools. So once it hits a certain tool life horsepower draw or tool life monitoring, however you want to get it set up, it will index onto the next tool, keep that system into production until there's a scheduled time where they go in and change out all those inserts at one time. So quick example, pardon me, I'm losing my voice. Quick example of return on investment. And again, I try not to go too deep on this because every application is going to be different based on your needs and what you're trying to do. But this is just an example of a typical way that we go through and look at how do we go about seeing the return on that investment. So your numbers are going to look different than these numbers. But again, just something I want to put up just to kind of have the wheels turning and understand some of the things that you could look at. So certain things that you need to compare 100% production versus what your actual net production is. And then looking at where is your downtime coming from. And again, that's where a lot of the monitoring system can come into effect to see why is that spindle stopped. And again, I'm a big fan of collecting it automatically. However, I grew up as an old school machinist, and we did this many years ago without having computers tied to the machines. We had a white paper set out there and Sharpie markers, and we would write down as soon as that spindle stopped for any reason, why was it? And we would trend that over a course of a couple of weeks and then find out, okay, what's repeating here and what's the low-hanging fruit that we can attack and try to drive that. So finding out where you're going down, and then taking a look at how does this compare, how we're doing it currently versus how we would do it in an automated system. So this is just, again, a typical scenario, 2 machines, 1 operator, parts coming in, parts going out. A man running the machines versus having it robot attended. So in this example, we're looking at 2 machines, 1 operator, excuse me, 1 operator per shift, 8-hour shifts, working 2 shifts a day, making 250 parts, working 250 days per year. And then the scheduled labor hours on that one was 4,000 hours. Looking at production rate, parts per hour of 10, so that gives us 40,000 pieces annually. And then looking at the hourly rate, and these are probably low figures, but $15.50 an hour plus 50% fringes. So that comes out to $23.25. So then we start looking at the percentages of where our downtime's coming in from personal relief, tool changes, etc. So we're looking at total efficient loss on a manual type operation of 30% versus 10% in an automated cell. So then you look at where your productivity is. If you're running that 100% annual production, your net annual production on this example is 28,000 pieces from a manual cell versus 36,000 in an automated cell. So then when you calculate that up to come up with, at the end of the day, and this is where this conversation can go far away from just automation, but at the end of the day, what you're trying to do is figure out how much does it actually cost you to produce that part. So in this example, that part costs this company $3.32 to produce it manually, versus when we do it automated, it costs 26 cents to produce that same work. So now if you look at the investment side of it, you tie in the machine tool, the inspection equipment, the automation equipment, total capital investment is going to be more on that automated cell, obviously. So in this example, we're using $200,000 for the automated system. So that's added on to the inspection and the machine tool side. So you're looking at $525 versus $725. So your annual capital investment that's amortized is $105,000 versus $145,000. Net annual production, 28,000 pieces versus 36 pieces. Capital cost per piece produced, you've got a variance there, $375 versus $403. Pardon me, I'll grab a drink. So then as we continue to work down through those numbers, you add capital cost per piece produced, total labor and capital parts, $7.07 on a manual operation versus $4.29 in this same scenario as an automated system. So your savings on that per year is $100,000. And then there's additional savings, and these are unknown, so I've just kind of highlighted them as red. But you've got overhead cost per piece that can be looked at. But then you also have capacity on that machine tool. If you're driving your efficiencies up, you've got additional capacities, hopefully if you're doing things right. What else can you do with that from that aspect? Now, if you take that same scenario and add a third shift, your total parts produced jumped to 42,000 versus 54,000. So your total savings jumped up to 155,000 a year. So again, adding more lights out, more runtime, nets more revenue at the end of the year. And then again, you still have those same talking points about what can you do if you're driving your efficiencies up and you've got more capacity to work with. So in summary, automation, everything that I've talked about today, it already exists. It's already out there. This is not new, innovative things. It's not new stuff that's got to be engineered. Everything I talked about is off-the-shelf items that are proven and can be implemented today. So whether you're talking about a gantry system on a lathe that's coming from an OEM, or you're talking about a robot-fed custom integration system, all the components that I just worked through, all the way down to software, monitoring systems, things of that nature, that is all off-the-shelf items that's proven technology. There's zero risk. So when you're talking about managing a business, managing your business, that risk mitigation is huge. So everything I talked about, this is proven technology ready to be implemented. So have you ever considered automation? If not, take another look. Just because you tried something one time 10, 15 years ago, it didn't work, doesn't mean it's not time to take another look at it. So we're here to help everybody at Okuma, all of our distributor network, Gossager, Hartwig, Morris, Arizona CNC, EMEC, Thomas Skinner, HEMEC down in Mexico, everybody that's within our group, we're here to help you move your production and your productivity and your profitability up to the next level. So if there's anything I can do for you, please don't hesitate to reach out. Brent, that's all from me. I'll turn it back over to you.
Thank you, Wade. We do have a few questions, and to our live audience, if you do have any questions, this is your opportunity to type them into the questions box. Let's see, let's start with the first one here. Wade, what are areas you experience that people tend to overlook when it comes to integrating automation?
Areas people overlook. I would say a big one is actually maintenance, maintaining the equipment. So they do a lot of legwork up front on the chip cutting side of it. They get their processes down. They've got CAM systems that's accurate, delivers great tool paths. They get that side of it down pat. They get it into production, and then they don't keep up with the maintenance side of it. If you're running cast iron, do you have the proper chip conveyors? Are you using cyclonic filtration to get the sludge out of the system before it gets into the coolant tank? If you're running, again, a lot of times when you go into an automated system, you're increasing your volume that you're used to running through that system. So your maintenance that you used to do, every 3 months, 6 months, all of a sudden may have to be every 2 months, or you need to get systems in place that's taking care of the chip, swarf, sludge, things of that nature, so you're not creating that downtime further down the stream. Does that make sense?
It does. Let's move on to the next question. Machine monitoring software. Do you have any advice on how folks or customers can use this to help drive their own efficiency?
Yes, that's a big one. That's that's an interesting topic. I go to a lot of trade industry events. I see a lot of companies that have monitoring software on the market, third-party systems. We work with a lot of them. They're all great software. The hard part is getting customers to rationalize sometimes where do they get the return on that investment. Once they get their machine connected and they're looking at it, now what do you do with it, right? You can extract an enormous amount of data from machine tools these days. How do you break it down to something that's actually usable? So the thing I like to look at, and I look at it from a business perspective, at the end of the day, efficiencies are great, but it's not just about turning a machine that's running 34% to 90%. Sometimes you really need to look at what is your financial efficiency coming out of that cell. So people get so programmed that, my machine's in the red, I got to make it green. I got to take it from 30% to 90%. They put a lot of effort into moving a cell that may not have that big of a revenue stream, where at times they may have an automated cell already that's running 80% efficiency and they're happy. They think that thing is cranking. But if you take that same cell and put energy towards it and take it from 80 to 85%, your financial return on that may be far greater than the one that's running 30%, just because the revenue stream is different. So the first thing I would advise is, understand what's taking place on the floor, but also what is taking place from a revenue standpoint, and which cell, as you're looking at it, as you're looking at these efficiencies, what is going to move the needle for the company the largest.
All right, we have kind of a comment and a question. Great presentation. A lot of the automation you showed was for smaller parts and mills. What would you recommend for larger machines, for instance, 10-foot square plates that robots might not be able to pick up?
Excellent question. And that's actually something I need to take note of, because I never actually thought about that in this presentation. These are sometimes the blind spots that you get into when you live this stuff. So large parts, if you ever get the opportunity, and I don't know if you're an Okuma customer or not, doesn't matter. If you ever have an opportunity to go to Japan and go through our newest facilities, they call it Dream Site 1 and 2. We have large double column machines. These are 3.5 meters between columns, 6 to 8 meter table bed lengths, and they're all automated. But on that, we use Fastums FMS systems, and we also use, it's another brand, I'm sorry, my mind's, Daifuku is another FMS system that makes systems like that for these big type systems. So we've done a lot of work from that aspect, primarily here in the United States. I keep throwing Fastums names out there, but they are a company that we do a lot of work with on the machining center side when it comes to FMS type systems. When you get into large work, I'm assuming, when he's talking 10-foot plates, he's probably talking mill work. So FMS systems, shuttling those pallets in and out, being able to set up the work outside of the machine tool to take that setup time out, so your only downtime is actually shuttling one pallet out, shuttling the other one in, getting that spindle back up and running would be, without seeing his work, that's the best answer I could give right off the cuff.
Wade, this question kind of makes a statement it's kind of embedded in the question that you may or may not agree with. What makes takt time higher in multifunctional machines?
Very good question. What makes takt time higher? So one quick one is the tool change time. So on a turret lathe, the tool change time is a fraction of a second to go from one turret station to the next. These are servo-driven turrets, very small movements, very fast. When you are working on a mill turn style machine, and there's exceptions to every rule, but if you're using flash tools where you're indexing the spindle to get to a different cutting insert, that's going to get you closer to what a turret lathe would do. But if you've got to run up and do a tool change, like a machining center where you're using a double gripper arm and you're grabbing another tool holder and swapping it out, that timeline to get, even though your rapid rates are incredibly fast these days, you're still taking time where you're getting that insert out of the cut, running up to that tool change position, doing the tool change and running back down. Those incremental items add up over time. Depending on the size of the machine, sometimes acceleration, deceleration rates vary. So for us, and again, I'm kind of painting a broad brush stroke, so I'm going to talk from an Okuma perspective. Most of our mill turn machines, where we fit the market really well, it's generally bigger type items. We're usually looking at larger size machines. So sometimes the spindle may be bigger. We've got a little slower acceleration rate and deceleration rate to get the spindle up and down to full speed versus a 2-axis lathe that may have a smaller spindle bore, things of that nature.
Another question, do you monitor spindle condition for bearing life?
We do. So there's a couple of different things. We have some AI software that monitors spindle bearings on the newest version of our horizontal machining centers that's coming out. But there's also other ways. I manage our Partners in Think program here at Okuma as well. We've got several partners that we work with that do similar things. Karen Engineering is one that has very, very solid vibration monitors. So even if you're working with, if your machine is not an Okuma, for an example, maybe you're running, brand X machine, whatever, or an older machine, Karen Engineering would be an avenue that you might could look at that could possibly retrofit to what you're currently doing. But yes, those are things we monitor. We actually have 9,000 data points in the machine that we monitor. It's sometimes mind-boggling what you can extract out of these machines these days. But we monitor vibration in various areas: ball screws, linear guides, spindle bearings, things of that nature.
Next question is kind of a general question. How long does it take to integrate a robotic solution?
Okay, so that's a little bit of a loaded question because it's going to be different based on the process that's taken place. So the load and go system that I talk about is a kitted up system. Literally, we just had one set on the floor and up and running on a machine in 4 hours. From the time they put a pallet jack under it, rolled it out to the machine, got the pallet jack out, and started installing it, they were making chips in 4 hours. That's the extreme side of the scale on the good scale, right? Now, when you look at like that pipe handling system where the cutting process is real simple, but the robots, I think there's 5 or 6 different robots in that cell. That takes time. That takes time to get it integrated and all the handshaking worked out. All the gauging and things like that. So that's where I can't say that's a 3-day process, right? That's going to be very dependent upon the process that the customer is doing.
Next question, we're about done here, but does Okuma only work with one brand? I think you might have answered this already.
Okay, yeah, that's an interesting question. So we don't work with one brand from an automation standpoint. Okuma, what I'll say, Okuma proper, and you'll notice all my slides has Gossager on the slides. From a robotic integration standpoint, our robotic integrator is Gossager Automation. So that's our largest distributor. We work extremely close with Gossager throughout the nation. They virtually do all of the integration from that aspect. Having said that, we are a open platform. So our machine, our control, if you're using a Yaskawa or a ABB or Fanuc robotic, doesn't matter to us. We've got an interface and we've got an open control system. We can communicate to anybody's. Running a universal robot, we can communicate to it. So we pride ourselves on the control being capable to be open to connect to whatever you're doing. We do a lot of work. Aroa is a great little pallet system for machining centers. So there's a lot of different avenues that we work with, even going, talking about fasteners, for an example. We can work with basically any flavor that you're looking for.
All right, we have time for one more question, and let's see, that is going to be, outside of pallet pools, are there any other automation built by Okuma directly? Or Okuma Direct, my bad.
That's a good question. And I don't touch on it in this presentation. I probably need to update the slide based on this. We do have a machine that's called a MUS600. We debuted it at IMTS this year. And it's a unique machine in that it transfers the part from one machine to the next. So it kind of has built-in automation in the machine itself. So we have a very simple loading system on the outside, and then it will transfer from one trunnion to the next trunnion, just like a lathe would transfer from a main spindle to a sub-spindle. It's a small little 5-axis machine. And then we are coming out, it'll be late fall this year, with a system. It's called an Armroid, and it's a 4-knuckle robot that's all built by Okuma, and it mounts inside the machine. Depending on the model, it's either beside the workhead or it's over the top of the workhead. But that runs AI technology from the programming standpoint. Has 3 end effectors that will grab parts, load the part, or it has coolant nozzles. It has a little steady rest to run to dampen work if you're doing shaft work, to have work support, things of that nature. So that's a very interesting unit. We don't have that one at our facility in Okuma yet. It was debuted at GymTOF this last year. So we'll be getting our first one here in the United States towards the fall of the year.
Okay, very good. Thank you, Wade. That concludes today's presentation. I want to thank Wade and Okuma for making today's webinar possible. If we didn't get around to your question, please feel free to email Wade directly at wanderson@okuma.com. Again, that's wanderson@okuma.com. And thanks to everyone for listening in. You should receive an email with a link to the recording soon. I'd also like to invite you to our next Modern Machine Shop webinar on improving production efficiency by looking beyond utilization data. That webinar takes place this coming Tuesday, May 14th. Thank you for your time and enjoy the rest of your day.